Now you are able to see my screen, right?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so now yesterday we were looking, this is elastic linear hardening model, right? Now, if you look at this, let us say you are talking about a stress at this point, the equation of line OAB. So equation of line AB can be written as sigma minus sigma naught divided by epsilon minus epsilon naught is equal to delta times E. What this delta is some constant between 0 and 1. If it is 0, then this slant line will be elastic perfectly plastic. Okay, so that is how, so it will be less than 1 because the slope, if it is equal to 1, then this will be, sorry. If it is equal to 1, so this will be 0, comma 1, less than, sorry, less than 1, the delta value. If it is equal to 1, it will be same as E. If it is less than 1, so you can see that the slope of this line is smaller than E. That is why it is delta times E. Okay. Now you can write this relationship as you can also write epsilon naught is equal to sigma naught by E. Can I do that? Because this is my epsilon naught. Now, if you have to write the generic expression for the constitutive relation, I can write sigma is equal to E times epsilon if sigma is less than or equal to sigma naught. And now I have to write sigma if sigma is greater than or equal to sigma naught. This is what is to be satisfied. So sigma minus sigma naught is equal to delta E times epsilon minus epsilon naught. Can I do that? That implies sigma is equal to sigma naught plus delta E times epsilon minus delta E times epsilon naught. And what is E times epsilon naught? E times epsilon naught is sigma naught. So that is can be written as sigma naught into 1 minus delta plus delta E times epsilon. That is my stress if sigma is greater than or equal to sigma naught. Right? There are two conditions. So I can now put them together. Sigma is equal to E times epsilon if sigma is less than or equal to sigma naught. Sigma is equal to sigma naught into 1 minus delta plus delta E times epsilon if sigma is greater than or equal to sigma naught. And sometimes, as we have said, we will write the equation. You can write the constitutive relation can be written as sigma as a function, some function of epsilon, or epsilon as some function of sigma. Both of them are the constitutive relations. That describes the behavior of the material. So you can also write from this expression, you can see sigma minus sigma naught by epsilon minus epsilon naught is equal to delta E. That implies epsilon minus epsilon naught is equal to sigma minus sigma naught by delta E. That implies epsilon is equal to epsilon naught plus sigma minus sigma naught by delta E. But we know what is epsilon naught. Epsilon naught is sigma naught by E plus sigma minus sigma naught by delta E. Now, if you look at this equation, this is like I am writing epsilon as a function of sigma. If you look at these two equations, then I am writing sigma as a function of epsilon. Right? They are interchangeable, completely interchangeable. I think yesterday we had difficulty seeing how this equation has come about. Right? Is that clear now?
Sir, one follow-up question.
Hmm.
In the sigma equation, instead of sigma naught, since we are writing it in terms of epsilon, should we need to substitute for sigma naught in terms of E epsilon?
But sigma naught is a material property, right? Sigma naught and E are material properties.
Okay. Okay.
They are constants for your material. You could write, say, sigma naught is equal to E times epsilon naught. Again, epsilon naught is what? It is not epsilon, right? It is yield strain.
Okay. Okay. Thank you.
Sir,
Yes. Ah.
if you slightly go up, can you slightly go up, sir?
Yeah.
No, sir. Slightly come down, sir. Yeah, here sigma is equal to sigma naught plus into 1 minus epsilon plus delta E into epsilon. We are converting epsilon naught to epsilon. How is it happening, sir?
No, I am not converting epsilon naught to epsilon. I am saying this quantity E times epsilon naught is equal to sigma naught.
Yeah.
If I do that, then what I have? I have skipped one step in between. So let me do that step also. Then that is equal to sigma naught minus delta sigma naught plus delta E epsilon.
Oh, okay. Okay, sir. Got it.
That step I missed. I did not write. That's all. Okay. All right. So now we will move on where we have discussed yesterday. Okay. So you're able to see the screen, right?
Yes, sir.
So all this we have discussed in the last class. And then I have talked about the effective strain. Is there everyone followed that? Are there any questions on that?
Sir, we can follow, sir.
Yeah. So all that we have done, and we have also looked at the case of plane stress case, but that's okay. Now let us look at the idea of 1 minute. I don't know why am I not. Maybe I will show it from my. I'll share my. Okay. So now I am going to talk about the unloading cyclic loading. So if you look at this particular figure, we are doing strain control loading. And if it is an elastic perfectly plastic material and an elastic nonlinear hardening material with several, it's a sequentially linear, right? Piecewise linear. This is what we call piecewise linear, but it's a nonlinear response. Now on the top, you are showing the strain input. Let us say you have loaded the material in strain, in positive strain, and then you are unloading. That means the strain is, as a function of time, the strain is increasing up to a maximum value, some value, and then again it is unloaded. That means the strain is reduced. When it is completely unloaded, it will go to 0, but here it is only partially unloaded. If the partial unloading, that means the delta epsilon, is less than 2 times epsilon naught. What is epsilon naught? So for example, if you take this material, if you are loading up to here, that means you have gone beyond. If it is elastic, perfectly plastic material, then let us say this is epsilon naught comma sigma naught point, that is your yield point. And if you have loaded this up to some strain, let us say up to this strain, corresponding to the strain, that is the point. That means it has actually yielded. At that point, what you have done, you have reduced the strain. That means you are unloading the system, so it will unload like that. But your unloading is not going to a very high value. It is less than 2 times epsilon naught. So 2 times epsilon naught, if you remember our idea of unloading, right? When sigma, when it is unloaded, if your delta sigma is less than, if the change in sigma is less than 2 times sigma naught, the yielding will not occur. Only when it is beyond 2 times sigma naught, then the kinematic hardening occurs in the reverse direction. Otherwise, if you have unloaded up to here and then you are reloading it, then it will go back along the same path. So the same thing that we are trying to do here. If your strain, it is like exactly like what you would see in stress. Let us say this is time, that is strain. You have increased strain up to some value, and normally if you reduce and if you do the cycling, right, like that, this is repeated loading. But in this case, what he is doing is, instead of completely cycling, it went up to this value and then unloaded only up to this point and then reloading again. Okay. So this during unloading, if you go to a certain value, if you go to a certain value, that delta epsilon being less than 2 epsilon naught, that means you are not initiating any plastic deformation. Right? So, and hence when you unload and then after unloading again, if you reload, the path will be completely elastic. Is this point clear? Because in the reverse direction, the yielding happens only when the change in stress value is greater than 2 times sigma naught, or in terms of strain, it should be 2 times epsilon naught. But is not less than 2 times epsilon naught, then it will not plastically deform in the reverse direction. And as a result, there will not be any plastic deformation during this process, and hence it will continue to, if you reload it, then it will follow the same path because it's the elastic path. Now let us look at this scenario. In this scenario, what we have done, loaded, unloaded to a value, that means delta epsilon, that means from here to here, the distance is greater than 2 times epsilon naught. That is like this. So if it is greater than 2 times epsilon naught, this is where yielding starts, but your strain is up to here. So your reduction, you have actually strain has reduced from, you have started unloading from here and up to here. That is your delta epsilon, isn't it? That is what we are talking about. If that value is greater than 2 epsilon naught, what is 2 epsilon naught? This distance is 2 times epsilon naught. This delta epsilon, since that is greater than 2 times epsilon naught, then the plastic deformation takes place. And whatever, because it is elastic, perfectly plastic, there won't be hardening. The plastic deformation took place. But then after that, what happened? Again, you are reloading. So then again, reloading means it will first elastically deform up to here. And if you have loaded sufficiently large, beyond that strain, because it is elastic, perfectly plastic, again follows the same path. as if this loop did not even occur. So it will continue to do the same path. So this is what we call hysteresis that happens due to Boschinger effect, as we have discussed. Now, this is a scenario when you have fully reversed loading. So you have gone from 0 up to certain strain, right, up to here. So if you have gone up to here, then you will have deformed up to some plastic deformation. Then you are unloading, but you are also going into the negative strain, right? You have unloaded and you went into the negative strain because it will start plastically deforming, because this value delta epsilon is much larger than 2 epsilon naught. Then as soon as it reaches 2 times sigma naught, when the moment delta sigma reaches 2 times sigma naught, then the plastic deformation takes place because you are continuously loading, and this is elastic, perfectly plastic material. The strain happens in this direction. So this from here to here is the distance from here to here. You can see that this is your epsilon axis. Here, this is your epsilon axis. Can you see that?
Sir.
And then again, you are reloading. So when you are reloading, you will go and then trace the same path. So this is initially there is no loading. When you want to do the cycle between plus epsilon and minus epsilon, first you have to go from 0 to plus epsilon. That is this path. After that, you are cycling between them, and hence you will continue to do this many times. Okay. This happens when it is elastic, perfectly plastic. But now, if you have a nonlinear hardening model, what you will have is up to epsilon naught, there will be elastic deformation, and then you have plastic deformation. And again, if you take the same strain cycling, it will unload, but even before it reaches plastic deformation, you are reloading, so that it will be elastic. So here it is no non-hardening, that is why it will be straight line, horizontal line. Because it is hardening, it follows the hardening law, depending upon sigma naught 3 and sigma naught 2 and so on, right? Depending on the material property. But then if you are loading, not fully reversed loading, but you are going to such an extent where delta epsilon is greater than 2 epsilon naught, you will see that it is again non-linearly hardening, but this kind of a loop again observes. And here you see that it is not a horizontal line, it is actually a slanted line, which is dependent on these E3, E2 and E1 values. Because that slope, you know, this slope is delta epsilon, as we have seen, that is E1, E2 by E1 plus E2. If it is 2 springs, if it is more springs, then that will be much more complicated. Similarly, if you have fully reversed loading, fully reversed strain cycling, then you see that the stress strain path will show this kind of an hysteresis loop. Is this clear? Now we are coming slowly to fatigue loading. Imagine how many cycles of loading that you are doing, how the life changes is what we wanted to understand. But in order to understand, we need to first understand the stress strain response when you do the cyclic loading. So before that, we will try to understand the cyclic stress strain behavior. Let us say you have a component. Here we are doing a controlled constant strain cycling. What is the meaning of that? You are cycling between, you are going from 0 to say epsilon b and epsilon b to this point. Let us call this as point E, right? So you initially loaded the specimen up to this strain. Now you are unloading between this epsilon max and to epsilon min. So these are the strain range. From this strain to that strain, you are cycling. This is what we call constant strain cycling. You will do this cycling and then you will realize this is basically, you understand why it is happening like that, because as far as the Boschinger effect is concerned, your yielding happens at a point C much before point A. A is your yield point, let us say. It is at point C and then it continues because you are loading in the this thing, compressive regime. And then again it goes, it's a fully reversed, in some sense it is fully reversed loading, right? Because the distance epsilon min is equal to epsilon max, magnitude wise. Okay.
So,
Yeah.
sir, in this sketch, could you just mark up that 2 epsilon naught? I mean, the second case that we discussed in the previous slide. Could you just mark up?
So what happens
where
is,
the
let us
loading-
say OAB is initial loading. Let us say that is my yield point. Okay. But my yielding might occur. So on unloading, yielding occurs at a lower stress C in compression due to Bauschenger effect. It may occur somewhere here. This is your actual yielding, but in the tension. But in compression, the yielding occurred at much lower stress. It did not wait until point A.
Okay.
So why is it happening here? Because let us say this is sigma naught. The moment this distance becomes 2 times sigma naught, that is when yielding occurs, right? That is what kinematic hardening talks about.
Yeah.
Okay. Now, if you carefully observe, this is what is entire strain range. Like you had a stress range, now you have strain range. So if you would plot as a function of time, strain as a function of time, it is going to a maximum value and a minimum value, maximum value and minimum value, maximum. So this is your epsilon max, this is your epsilon min, and what you can say is that epsilon max is equal to minus of epsilon min. And this is what we call delta epsilon or strain range. Very similar to stress range. And this is what we call epsilon A. That is equal
Strain
to
amplitude.
delta epsilon by 2. That is my strain amplitude. Right? Here, is it a fully reversed loading or not? This is fully reversed loading because epsilon min is equal to epsilon max. And you can see that the stress is varying from this delta sigma by 2, delta sigma by 2. Right? The stress range is this and strain range is that. So the dimension of the hysteresis loop is delta epsilon and delta sigma. That represents the dimension of the hysteresis loop. So this is how. Yeah. Any questions?
No, got it. Thanks, sir.
Yeah. So now, if you look at this, this is how the hysteresis loop that we are talking about. This is the total strain range for a corresponding stress range. So total stress range corresponding strain range, and this is what we call the total strain range. If delta epsilon can be decomposed into 2 parts. Elastic strain range and plastic strain range. Elastic strain range is given by delta sigma by E because this is when you are unloading, this is the recovery of the elastic strain. So that's why you take the slope and that is your elastic strain range and this is your plastic strain range. Okay?
Sir, one small question here.
Yes.
The curve, as I cycle in the fatigue actually, due to Boschinger effect, you are not going to have the same curve, right? It will be shifting, right? Because of the yield point is going
That we will talk about. That happens because of the reverse yielding, because the dislocations I told you yesterday.
Yes.
Then after some time, what happens is you will see that this curve, if you continue to repeat, it will not follow the same path. But after several cycles, what happens is it saturates. We will see that in the coming slides. Okay.
The curve here is only for one cycle, right? Or it's for...
If I have drawn for one cycle, or you can assume that it is drawn after reaching to saturation.
Okay, got it, sir. Got it.
However, this cyclic, there will be a modification to the structure due to cyclic loading, as the plastic strain is not reversible. And depending upon the initial state at the beginning of the loading, the material may undergo cyclic hardening or cyclic softening, or sometimes cyclically stable. What is the meaning of that? Let us look at this. Let us say you are doing, this is your strain cycling, right? Here is a strain control experiment you are talking about. When you are doing this strain cycling, normally what should happen? Your strain cycle from this strain to this strain. When you increase the strain again, you have to observe the same stress, right? But in some materials, you don't observe the same stress. So as a function of time, if you are plotting, it is initially at this particular time, it went to this stress. And by the time here, it came to here. And again, when I increase, normally it should have come here if it is not hardening. But you will see that it is actually changing. There is a material, the material is getting hardened. So as a function of time, under constant strain amplitude loading, if your stress is changing at each and every cycle, such a material is called cyclically hardening material. If you look at the stress strain response of that fellow, it looks like that. This is how it started. And in the next cycle, it will go there. It is not reaching the same stress. The stress is increasing. All right. And again, in the next cycle, it will go to higher stress. That means this stress value is increasing at each and every cycle. And that is what we call, this is that stress value rise. And such a material is called cyclically hardening material. You also sometimes have cyclically softening materials. That means the stress may not increase, but rather decreases. And when cyclically softening material, initially it is loaded up to here. In the next cycle, when you go, you will have the stress reducing. Further again, if you go, and stress further reduce, as you can see here. Such a material is called cyclically softening materials. In both of them shows hysteresis loop, but there will be cyclic hardening or cyclic softening. But these hysteresis loops, after so many cycles, if you do say for 100 cycles, what happens is the system achieves an equilibrium, and then there won't be any change in the cycle. So they will all reach some certain equilibrium. If you look at this particular figure, which is for a nylon 6x6 13% glass fiber, the cyclic loading is done, right? Here you can see stress. Is this a cyclic hardening material or cyclic softening material? This one.
Softening.
Cyclic softening material. After some time, you see the hysteresis path is not changing. It is facing the same path. This happens typically for metals after 100 cycles. So whatever curve that I have drawn here can be seen as saturated curve. Okay. Now, when I am talking about delta epsilon, that is total strain range, can be seen as elastic strain range plus plastic strain range. So the total strain range can be written as elastic strain range plus plastic strain range. But normally we don't usually work with strain ranges, stress ranges in stress life approach. We worked with stress amplitude. Similarly, here we can work, instead of working with strain range, we can work with strain amplitude, which is basically nothing but strain range by 2. So I am dividing this entire equation with that, with 2. Then you have delta epsilon by 2 is what I am calling it strain amplitude, or epsilon A is equal to delta sigma by 2 is stress amplitude by E, plus delta epsilon P by 2 is plastic strain amplitude. So many materials, if you look at this stable hysteresis loop after so many cycles, usually symmetric in tension and compression for metals. But for some materials which have extremely high fracture strength in compression compared to tension, such as gray cast iron, this can be asymmetric. It is not necessary that it should always be symmetric, but for most of the metals, the hysteretic loop, which is saturated one, will be mostly symmetric for tension and compression. Okay. So now, if you would plot, for a given strain amplitude, right? You do the stress strain curve. After some time, it will reach saturation. Let's say something like that. You will have a saturated hysteresis. This is for one specific strain amplitude. So if you do, let us say, this line is for a particular strain amplitude, this loop. Similarly, this loop is for another strain amplitude. Like that, you have all these for different strain amplitudes, you have plotted these loops. Now, if you connect the lines passing through these peaks, these junctions where the reversals are happening, that line, both in tension and compression, if you connect that line, that passing through origin OA, BC, DE, FED, OA, BC, this line is what we call cyclic stress strain curve, right? Whenever people are talking about cyclic stress strain curve, that actually is a stress strain curve obtained by plotting the hysteresis, the line joining the peaks of the hysteresis stress reversal or strain reversal points for different strain amplitudes. Is that clear how we got this curve? So for example, if you take a material, you started from zero strain and you are going for maximum strain here and minimum strain here. So then that particular loop, what do you call a hysteretic loop is that for a particular strain, one strain amplitude. If you increase the strain amplitude of the same material, then it will go to B, and then so OAD A is for one particular strain amplitude, OBEB is for another strain amplitude, OBEB is for another strain amplitude. So if I have to write OADA for epsilon A1, OBEB strain amplitude true, OCFC strain amplitude 3. All these things you are plotting on a single sigma epsilon plot, and now you connect now you connect you're still able to see my screen, right?
No, sir,
Hello?
I'm seeing the phone.
No.
Oh, sorry. Right, I said corresponding to epsilon A1, that is OADA loop, corresponding to epsilon 2 OBEB loop, corresponding to strain amplitude 3, that is OCFC loop. Right, now you can identify, so these are all for different strain amplitudes. I have drawn the saturated hysteretic loop. And now when you do that for this material, if you connect the points OABC and DEF, then basically this the curve in blue is what we call cyclic stress strain curve. Is that clear?
Sir, one small question here.
Yeah.
For the first cycle, it will pass through O, but for the second cycle, it's not going to pass through O, right?
No. I am doing 3 different experiments.
Okay.
If I am doing first experiment with epsilon A1 as my strain amplitude.
Got it, sir. Got it. Now I got it.
Yeah. Any other questions? All right. So now this cyclic stress strain curve can be represented using a constitutive relation like this. And of course, you can write it in terms of strain amplitude instead of strain range, right? So it can also be written in terms of strain amplitude. Here n dash, the 1 by n dash is there, no? That n dash is going to vary between 0.1 and 0.2. And generally for metals with high strain hardening exponent, n greater than 0.15, they undergo cyclic hardening, and with less than 0.15, they undergo cyclic softening. Or if you know the ultimate strength of the material and yield strength of the material, If that ratio is greater than 1.4, that results in hardening. Less than 1.2, softening. If it is between 1.2 and 1.4, no, neither hardening or nor softening is expected. So if you look at typically for cyclic hardening materials, if you look at this is a 2024, these are different material systems. For this particular material, you can see this is uniaxial monotonic loading. But if you do the cyclic loading, you can see that the cyclic loading curve is above the monotonic loading curve, which means it is cyclically hardening material. All these things are cyclically hardening materials, whereas the figures on the bottom are cyclically softening materials. You can see that, of course, this guy also plays again cyclically hardening material, but these guys are cyclically softening material. So these are, that means these kind of materials do exist in the nature. Now, so what did we understand until now? Whenever you are doing cyclic loading under plastic deformation, because when it is elastic deformation, no problem, the path traced is the same. The problem comes only when you have plastic deformation. Under plastic deformation, if you are doing the stress reversal or strain reversal, the plastic deformation is going to happen at different points in tension and compression, right? And now you are operating between certain strain range. And now the question is, how do we assess my life, fatigue life? If I am operating my component between two strain ranges such that the strain range that you are operating, delta epsilon, is much larger than 2 times epsilon naught, or the corresponding stress range happens to be larger than 2 times sigma y. In those scenarios, you need to be worried about how it is going to work. So how do we, so that is what we call a low cycle fatigue, because your strains are going to be much larger, or the stresses are going to be much beyond the close to yield strength of the material, and hence you need to only apply the low cycle fatigue approach. And this is typically the case for several materials, several components in nuclear pressure vessels, because the loads that they are usually exposed to are much larger, steam turbines and aerospace components. They usually operate at very high stresses with potential plastic deformation. So one of the, like SN curve, one of the popular strain life approaches model is what we call Coffin-Manson relation. Here, this is given by epsilon PA, that is plastic strain amplitude. We know what is plastic strain amplitude, right? We have already seen. That is the reason why we have to understand the terminology there. Plastic strain amplitude is equal to some constant, epsilon F dash is a material constant, which is called fatigue ductility coefficient, and times 2n to the power c, where c is also a fatigue ductility exponent, whose values vary between minus 0.5 and minus 0.7, like A and B in case of S is equal to n power b. However, please note that 2n here are the number of strain reversals. Why are we using number of strain reversals? Because if you have one cycle, in one cycle you have two strain reversals, right? Because the strain, one cycle, the strain will reverse twice. That is why even in S is equal to A n power b, number of cycles, sometimes people use 2n to talk about number of stress reversals. Right? N is, so the 2n is the number of strain reversals, where one cycle refers to two reversals. And then, if you have a smaller or larger value of C, then you will have a smaller value of C, because if there is a negative exponent, you will have larger fatigue life. So this Coffin-Manson relation is very similar to S is equal to A n power b, but here it is stress amplitude. Here we are talking about plastic strain amplitude, right? So now one can calculate for this particular system, for the cyclic stress strain curve shown in the figure, sigma b is equal to 75 MPa, epsilon b is 0.000655. If epsilon f is equal to 0.3, and E is equal to 22 into 10 power 4 MPa. Determine elastic stress range, plastic stress range, and the number of cycles for failure. Epsilon F is nothing but epsilon F dash. Can you solve this problem? So the equation is epsilon F dash, epsilon, the Coffin-Manson relation is plastic strain range is given by epsilon F dash times 2 times n number of strain reversals to the power C. C can be taken as whatever they are saying, minus 0.5. So you take either C is equal to minus 0.6. We don't know that number, so you can take that and then try to find out. You understood what you need to do? We need to find out N. In order to find out N, you need to know what is the plastic strain amplitude. So using this data, you need to first compute plastic strain amplitude. Please go ahead. I'm giving 10 minutes so that you can carefully look at this and then find out what is plastic strain amplitude if you want to know. That is what is your plastic strain amplitude. If you can note down this figure, then this is giving you plastic strain range. Divided by 2 is your plastic strain amplitude, delta epsilon P. This is what this is plastic strain range. Divided by 2 will be plastic strain amplitude, that is epsilon PA. Can I go to the actual system?
Yes.
Yeah. So here this slope is E because it's elastic unloading. Yeah. Anyone solved the problem?
Two minutes, sir.
Yeah.
जी can sir
Yes.
sir 4.8 into 10 to the power 4 cycles.
So you are saying n is equal to
4.8 into 10 to the power 4 cycles.
Everyone got that number?
So I'm getting 2.3 into 10 power 6.
2.3
into 10 power 6.
Okay. Let's try to solve this and then. You're able to see the screen, right? With the writing pad.
Yes, sir.
So here we are saying sigma B is equal to 75 MPa. Epsilon B is 0.000645. Epsilon F dash whatever 0.3. And E is 22 into 10 power 4 MPa. Correct? So if I this is my E, right? Because that is elastic one. So if I go like that, and this is my delta epsilon elastic, that is my delta epsilon plastic. Correct? So how do I kind of delta epsilon elastic is equal to delta sigma by E. Can I do that? Delta sigma is 150 divided by 22 into 10 power 4. Correct? Therefore, delta epsilon P is equal to epsilon B minus delta epsilon E that therefore delta epsilon P is equal to epsilon B is 0.000645 minus 150 by 22 into 10 power 4. What is that value? What is that value?
5.768 in 10 power minus 3.
5.768
into 10 power minus 3.
Then, therefore, epsilon PA, plastic strain amplitude will be 2.5768 into by 2. 2.768 by 2 is 2.884. Yeah, into 10 power minus 3. Now, our Coffin-Manson relation says epsilon PA is equal to epsilon F dash times 2 times n power B or minus B.
So 1 by C.
So 3.68 into 10 power minus 5 is the delta epsilon P I'm getting.
This is okay. 1 minute. Let me check. Calculator. 150 by 22 divided by 1 by B 10 power 4 minus 0.0645.
In fact, minus.
That is correct. 3.682, right?
Minus
Sir,
3.68
strain will not
into
come
10
in
power
negative.
minus 4. Sorry, minus 5. I'm getting a negative value.
Yeah, but that we can take positive because the amplitude only, no?
Yeah, okay. 10 power minus 4. Sorry, minus 5.
Yeah, minus 5.
Minus 5, huh?
Yes, sir.
Yeah.
That is 1.841 into 10 power minus 5, isn't it? Correct? And I asked you to take B is equal to minus 0.6.
Yes,
Epsilon F dash is given as 0.3. Therefore, 2 times n is equal to epsilon PA by epsilon F dash whole to the power 1 over B, or n is equal to 1 by 2 times epsilon PA divided by epsilon F dash whole power 1 over B. That is equal to 1 by 2. Epsilon PA is 1.841 into 10 power minus 5. Epsilon F dash is 0.3 divided by minus 1 by 0.6. What is that value? Divided by 0.3.
Into 10 power 6.
Sorry, how much?
5.24 into 10 power 6.
Same only, sir.
That's what you told earlier, no?
Yes, sir.
Yes,
Correct.
sir.
So
4.8.
this is the number of cycles to failure. Right now, so whenever you want to get the number of cycles to failure in the case of strain control loading, for example, in the low cycle fatigue, so you use Coffin-Manson. Coffin-Manson is one of such relations. Again, here We are not talking about mean strain at all. Mean plastic strain is 0, isn't it? So that one needs to take into consideration. That is it does not account for mean plastic strain or mean strain amplitude. When the mean strain comes into picture, you need to use other models. Okay. So the answer is 5 point. Now, so this is your strain life approach. There is also other models like Coffin-Manson relation. This is also another model where if strain amplitude is given by sigma f dash by E into 2NF for B, because the total strain amplitude, earlier you have only plastic strain amplitude, but the elastic strain amplitude can actually be represented by our stress life approach. So if you look at that, this can be written as sigma A by E plus sigma A by H dash into whole power 1 by N dash, because epsilon plastic strain can be represented by this. So your strain amplitude, stress amplitude can be represented by your S is equal to AN power B. Your A is sigma F dash. N is 2 times NF power B. So this is also one of the relations. You can also use in this place AN power B. Plus, this is your Coffin-Manson relation, right? So when the strain, total strain amplitude you have to consider, then you have to take elastic part as well as plastic part. And if you look at both of them, if you look at carefully this figure, this is the strain amplitude and number of cycles to failure, right? If you are, if you take up an elastic part, that will be sigma f dash by E, and plastic part is given by this line. This is a log plot, as you can see, and the total is given by this curve. And you see that here there is a large strain amplitude, right? Because the strain amplitude is higher and hence life will be smaller. If the strain amplitude is larger, smaller, the life will be larger. And you will clearly see that as your strain amplitude becomes smaller and smaller, right? That means your plasticity in the material comes down. When the plasticity is in the material is coming down, the solution approaches your SN curve line. This is your SN curve line. If your strain amplitude is larger, then there will be more plasticity, and hence the solution approaches pure plasticity line. And the real life will be somewhere in between. So this is a complete picture. Earlier, what we have done is only taken Coffin-Manson relation, which relates only plastic strain amplitude. But now in reality, you will have both. And when the comparison, the relative fraction of this is much smaller than this, then only Coffin-Manson relation is okay. Otherwise, you will take into account of some hybrid approach where elastic part is dealt with as S is equal to N power B, and plastic part is dealt with as Coffin-Manson relation. And then sum total of that will be your actual strain life diagram. This is what we have: strain amplitude on the y-axis, life on x-axis. So this is what we call strain life diagram. Okay. So now you have a total strain amplitude, sigma A, stress amplitude. So for the data shown in this figure, obtain the constants for strain life curve. How will you do that? So you actually, this is your strain life curve, and you need to fit this data to the strainless curve and then get the constants, right? Like what we have done in the previous case. Any questions here?
No, sir.
Yeah. So I'm not solving the problem. I would like you to try solving yourself. So this is something that we have already seen. When you have at longer lives, you know that plastic strain is small and hence the elastic process governs. That is why the elastic line is there. At short lives, the plastic deformation dominates and hence this guy plasticity dominates. Then we define something called a transition life, where the elastic line and plastic line intersect each other. All right? That means this is equal to that. When you equate that, that life is what we call transition life. So the transition life corresponds to the state where elastic and plastic behaviors coincide, and the transition life is given by this equation. So if you have a given material, the material has certain properties epsilon f dash sigma f dash epsilon f dash e c b, all are material constants. So for a given material, the transition life locates the boundary between HCF and LCF. Left to this is LCF, right to that is HCF. You remember, for steels, you said 10 power 3 cycles is the boundary between HCF and LCF. How did we arrive at 10 power 3? We said 10 power 3 to 10 power 4 because it depends on the material. By now plugging in these properties of a given material, sigma f dash, epsilon f dash, E, C, and B are all material constants, then you will be able to compute what is NT. So for that particular material, the number of cycles of life required is greater than that, then you can actually apply HCF. If it is less than NT, then you can apply LCF. Okay, is this clear how you obtain the transition number of cycles? Okay. The strain life curves that we have seen are not really sensitive to surface finish and residual stresses, unlike stress life curves. That is why in the case of stress life curves, we have several correction factors, right? For surface finish and if there is any temperature and all these things. For strain life curves are not sensitive to that, but size effects are a concern. That means size factor is something that one needs to take into account. So the epsilon f dash that we are using should be accounted for with size ratio depending upon the value of D. So one needs to apply a size rejection factor called MD and then apply sigma FD dash is equal to MD sigma F dash, sigma FD epsilon FD dash, MD epsilon F dash. So that means the sigma F dash and epsilon F dash shown in this equations should be modified when there is change in size. And we also need to worry about the mean stress effect. So the mean stress effect can be dealt with very similarly, and this is what we call Marrow's mean stress equation. When you have a mean stress effect, you can use Marrow's equation for mean stress, and then that can be modified, and then this is your equation that you need to consider when you have a mean stress effect, wherein your mean stress comes in here. Okay. I think that is pretty much how you will deal with strain life approach. I will give you certain assignments so that will prepare you to solve the problems using strain life approach. And in next week, we will primarily focus on creep failure. Okay?
Okay, sir.
All right. Thank you. See you next week.
Sir, one small question.
For
the exam, the formulas that you had given, do we have to?
I will give almost all the formulas that are required for the exam. They will be included in your question paper.
Okay, thank you, sir.
Yeah.
Thank you, sir.
All right. Bye.
Thank you, sir.
Professor, please upload your handwritten notes.
Yes, I will do it by tomorrow. Yeah.
Yeah. Thank you.
Thank you, sir.
Thank you, sir.